right, so what's the first one, guys? Number 1. Okay, so give me its name. Don't spell its name. Sulfuric acid. Good. Okay, number 2. Anybody get anything different? Potassium biphosphate one. Potassium biphosphate. Okay. Number 3. Sodium what? Hydroxide. Good. Number 4. Lead 2 nitrate. Number 5. Calcium chloride. Good. Number 6. Ammonium nitrate. 7. Potassium acetate. Even though it says to cook, right? But we know it's potassium acetate. Just remember how you can rearrange something like with an organic oxide. 8. Magnesium chloride. And 9. Sodium carbonate. Okay, we got all 8 bioprocess elimination problems from those. All right, so you guys have a chance to finish up the error analysis, which you will have to just base it on the observations you made, not really any % errors or anything like that. So based on your observations you made, and just say, my assumptions of my observations made me, or guided me to this conclusion, however, it was incorrect, and then you can kind of explain possibly why. There's not really a right answer to the error analysis on this one, okay? All right, so in terms of notes, I did not actually print this one in your packet, my bad. So, can you guys take a couple and pass these back to me? But I printed them on separate sheet of paper, and it's a big piece of paper. Look at how many trees I'm showing for you guys. Great. Keep one for Darcy. All right, so you guys have written this down on the board, the blue stuff? Yeah, no? Yes, okay. There's extras. Alright, so I'm going to respectfully ask that you put your labs away for now. All right, guys, so stoichiometry with acids and bases, we generally just say, hey, we're doing a titration. So the stoichiometry aspect of it is more with reference to the application, which is usually a titration. So, that kind of is the acid-base difference. So you guys watched your pH calculation video. How do you calculate pH? pH equals negative log of H plus, right? Or hydronium, right? So I will write H plus, or I'll write hydronium. We'll usually use this in our same thing with OH or hydroxide concentration, right? So you'll do negative log of OH concentration. So something like that. But collectively, what we have to assume is that, well, if I have water technically kind of contains both of those ions. If it were to ionize, it ionizes to a very, very, very small extent by the auto-ionization of water. H2O plus H2O. One of them acts as the acid, one of them acts as the base. They donate an H plus. You're left over with hydronium hydroxide. It's a very, 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 very small amount. So that's what we usually just ignore the fact that even could occur. But in acids and bases with pH calculation, sometimes we just have to recognize that this is our baseline. This is what we kind of compare everything to. So H3O plus and hydroxide, they actually both are equivalent to each other since it's a 1-to-1 ratio, and they make a very small amount, which is 1 times 10 to the negative 7 molar. So that's so small, we generally ignore it if water is the only thing present, which in the end makes our assumption to be water with pH of 7. But what we do is when we multiply them together, so hydronium concentration times hydroxide concentration, that's equal to 1 times 10 to the negative 14. That should look familiar to you. That's in your pH calculation formula, right? So that just memorizing those is one thing, but figuring out where it comes from is a little bit farther for us. And so we call this KW, which is the dissociation constant for water. We will use this a lot, not just now, but in the future. It's Darcy. All right. So other than that, we do this for water. We could do it for ammonia too, because it still auto-ionizes just like water can, but we don't use it for the perspective of pH calculations in that sense. Okay? All right, so now back over here. We have titrations, right? The terminology that goes with titrations is something you're somewhat familiar with. Just a quick reminder here, okay? So volumetric analysis is the way that we talk about what a titration is actually doing. It's using unknown concentrations. What does bracket mean? Usually in molarity, right? So I will try to abbreviate that as we go. So you're taking known and unknown concentrations of two different species and volumes of those, and we're analyzing that. So volumetric analysis is using the volumes of those concentrations to analyze something about the other one, aka titration. That's what it is. So specifically in a titration, we are using like a burette, and we're controlling the volumes dispensed, which is why we read the burette as it is. If it says 0, it's a 0. If it's a 23.59, it's a 23.59. Don't you try to flip that burette and make it harder on yourself to read the measurements. The titrant is the solution that we call the known. It has two names, titrant or known, meaning we know its concentration. The analyte is the one we're analyzing. It's the unknown. So the terminology just comes into play now so that when you're reading questions, you're like, okay, I can rationalize what this means. It's the one that I know the concentration of. The other one is the one I'm concerned with calculating for. In terms of your pH curves, everyone has seen this, yes? Curves at least. Everyone who did a titration, like use the burettes in honors count. Okay, a lot of us have, but not all of us have. And I know some teachers even here didn't do them last year, just because time runs out in the year, and you guys want to do it if you can. So you guys have done titration with me, though. Okay, sorry, you used a burette and then ran your titration successfully, most of you guys, with your hydrogen carbonate lab. You guys will be doing another titration on Tuesday next week, so that's why we're going over this now. So the equivalence point on a pH curve with the labeling of the axis being pH and then volume added, the equivalence point is on the vertical section halfway up, okay? So the halfway point on the vertical section we call the equivalence point. But is that the end point? Yay or nay? The way I phrase that should give it away. Is that the end point? No. The end point is something that we kind of have to strategically find out by selecting an appropriate indicator for our reaction. Because you guys know this now. Hydrochloric acid, if that's our acid we're using, it's clear. Sodium hydroxide, if that's the base we're using, it's also clear. I can't tell when moles and moles have neutralized each other or if they're equivalent just by looking at the solutions because it's all clear. So I have to use something to indicate to me to stop the reaction or stop the titration. And what do I use for that? Dyes or indicators, right? Indicators have all these different names, and what are some of them that we already know? Say again? P something, phenolphthalein. What else? Methyl orange is the one we used. Litmus paper is one that doesn't give us, we can't really use it in a titration per se for solutions, but we can use it to dip into a solution and say, is it acidic or is it basic? It doesn't give us a lot more information, but that's the red and blue paper that turns blue and red. Any more? Cabbage juice isn't a universal indicator, right? It actually goes through probably 5 or 6 different colors. So that's useful to know the pHs, but not to say when to stop at titration. We like the ones that are one color in acidic solution and one color in basic solution. So when we know when we surpass that point, the color change occurs, we stop the titration. That is the end point. So definition though of equivalence point, we say acid moles equal base moles, but a definition of end point is just where the indicator changes color. We want those to be super, super close together. We have to select our indicators based on where we think the where we think the equivalence point will be. So we want these to be close, and if they're not close, then our calculations will be off. That is where error can occur in a lab. And then the terminology standardizing solution just means for us to take a solution, titrate it to the point where we can find the exact concentration. And a lot of times we do this with a substance called KHP. So potassium hydrogen phthalate, that's not phosphorus, it's phthalate. So we'll use this because it's it's a slightly acidic, but it's used to determine the concentration of, like, let's say sodium hydroxide, which is a lot of time the base that we'll use in titration. Okay, can I move on from terminology? Yeah.
It says the equivalence point is when moles are equal to moles
moles of acid equal moles of base. No, good point. That will only occur at a pH of 7 if it's a strong acid, strong base. It could occur at a different level if it was a weak acid, strong base, or a different pH if it were a weak base, strong acid. It does, say again? How do you know where it would change? So if you, first of all, you know your 6 strong acids, your 8 strong bases, so you could predict if it's above 7 or below 7. When we get into that month-long pH acid-base equilibrium, then you'll be good. Okay, so the calculations that'll come later, we're just going to predict first. Okay, so this is your typical setup, right? You guys have seen how this is set up. This is a line that's supposed to show you the differences if you have a pH curve between a strong acid, strong base combo or a weak acid, strong base combo. What do you notice about the strong acid versus the weak acid where it starts? So who's lower? Strong acid, which makes sense, right? It's delivering more H pluses to the solution. The pH diminishes and drops down closer to 0. Weak acids don't ionize very well, so they naturally start off at a higher pH because they're just not delivering too much H plus to solution. pH stays kind of high. But since I'm adding strong base, they both increase. They have a different progression of how the pH increases, which is called a buffer, but they both end at the same place. Why do they both end at the same place? What am I adding to this? Okay, I'm assuming it's a strong base, so I'm just going to put sodium hydroxide as my example. At the point of the equivalence point, which is like here-ish in the strong, but it's like here-ish, kind of, in the weak and strong base one. First of all, the equivalence points are different, but they end at the same place because I have now excess sodium hydroxide, which takes over the pH. It definitely controls the pH from there on out since it's in excess, and therefore it pushes the pH to very basic. Yeah. And if you over titrate, actually, and your color changes to like a really dark color, you can see the phenolphthalein, right? It gets really pink, which we've seen in real life, but you want the really light pink, which is at the equivalence point. Can I move on? Okay, I can read your minds. All right. So these are just some examples of what these molecules look like. You don't have to memorize these. I just want to give you the complexity of them. Methyl red is an indicator. Basically, it has this huge structure, and this little H over here, which is a carboxylic acid H, is the H that we can manipulate to make it seem acidic or seem basic. Bromothionyl blue, it's H. I don't know what it is right here. No, that's an alcohol. K. So I think it's one of these that actually gets the H when it gets protonated. But it's a very complex structure. And then here's phenolphthalein. Down here, they're super complex. But what we do is when we manipulate by addition of H's or removal of H's, they change their color. And that's why we use them specifically, because despite them being so complex, we can manipulate their H pluses being protonated or deprotonated very easily. Yeah.
Are we going to ever have to know how to read those or know how to write those?
Not this complex. Your organic stuff will not be this complex. Okay? I have forgotten a lot of my organic. I cannot tell you this right now. Yeah. Okay, so it's above both of our pay grades, but I did some research on this. Basically, they're called conjugated systems. Double bond, single bond, double bond, single bond, double bond, single bond. There's a cascade of double, single, double, single. When wavelengths or when light hits it, the electron energy travels through those double, single, double, singles, and when they come back off with lower energy, they're a different color, or it can be absorbed all the way and never give off a color. It's a little bit above our pay grade. All right. Based on electron energy levels. Okay, so I've set this one up for you guys. I want you guys to tell me, in terms of how this is running, who's the analyte and who's the titrant. Try not to show you all my answers. What are we starting with in the beaker or in the flask? Base, okay. Okay, and then we're dropping what? Acid, and the pH continues to drop. So in the flask, generally, who is that? Is that the inlet or is that the titrant? Generally, it's the inlet. So the thing we put in a certain volume of, but we're like, we don't know the concentration. And then you drop your titrant, which you get the volume, and assumingly, you usually know the concentration of the titrant as well. And then we can take that information and then find the inlet information. So similar story, though, with the equivalence point, it's halfway point, no matter if the vertical section is coming from the top down or the bottom up. Okay, we're starting with strong stuff right now. And then this is a really dark image, like the lights off. Base is a polyprotic acid. What's polyprotic mean to you? Polyprotic means what? Poly, many. Protic, proton, which we call what H plus is. H plus is technically just a proton because it's lost its only electron it ever had. So polyprotic systems are like diprotic acids or triprotic acids. So this example is a triprotic acid, which is phosphoric acid. And so it actually has two equivalence points, technically three, but it has two because the first one drops off its first H, leaving us with the H2PO4 1 minus. The second one undergoes another deprotonization, or D taking off one more H. So it undergoes the deprotonization and makes HPO4 2 minus, and then so forth. The last one in this particular one is not really observable, but it could take off its last H and then continue a little bit more. Yeah. Because the pH is getting really high. So you're seeing your 11. It might get to 12 or 13, but it doesn't make a very good swoop to show us the equivalence point. It kind of just like has this incline because the pHs are so close. These just give you a bit better inflection because the pHs are farther away. Yeah. Because it's not strong. So the fact it's not strong, the first deprotonization is an effort. And then the second one is even more of an effort, like it does not want to give up the H plus based on its strength of bond. And then the third one's like, heck no, I'm not giving up this H plus. I really want this H because I'm strongly bound to it by the phosphate. So it's just unlikelihood and unlikely to give up H's. Yeah. It actually gets more stable because the stronger the bond, the more stable the compound is. Yeah.
So if it was a strong acid that you were titrating, but everything was good?
Oh yeah, the H's would be off before you started because they actually never connected in solution. They're already 100% ionized.
So that one would hurt the line is like
Yeah, on over here. So good point. It's a very quick increase or decrease of pH because if you drop off H's, your pH drops. If you neutralize H's, like a strong base would when using its OH's, it's going to increase pH very quickly. So it's much more exponential in terms of strong than weak, or even weak involved at all. Good points. These are all things we'll talk about more later too, okay? Now we're going to do calculations. I think I have one more slide first and then we're going to have calculations. Oh, so here's, I wanted to see your thoughts on this first. Looking at the heart, tell me, let's make up, or I gave you a reaction already. I give you HCl and NOH just to get us started on strong. Which species or ion is most prevalent in the heart here area? Say again? Is it HCl? We want to say HCl because that's where we're starting, but what is it now? It's the ion form, right? H ion and Cl ion. So the most highly prevalent species at this section is not just HCl because it has 100% ionized itself already. It's a strong acid. That's what's present. Okay. As we add base here and here and here, what is that base, which is sodium ion and hydroxide ion? What is it doing with these? Okay, so the H plus and the OH are going to come together and make water, right? So as we go up, you're telling me what's happening to the H plus concentration. It's going down because its natural bond is going to be with the hydroxide to make water. So as the H plus concentration goes down, what's happening to the pH? It goes up because it's an inverse relationship. Okay, so we're adding this. What's true here at the equivalence point? Moles of H plus equal moles of OH minus, right? So basically at that point, neither of those are present. What have they formed instead? Water. Okay. So water is a pure liquid, so where it doesn't ionize to an appreciable extent. We know a teeny bit does, though, because that's how we get the information there. So water is present here. What else is hanging out here in solution? Sodium ion and chloride ion, okay? So both those are hanging out in solution, just big chilling. They're not really doing anything. They're spectating. And then as I continue up, I'm adding more of what? I'm adding more, say again? Sodium hydroxide, right? Okay, so I'm adding more Na plus and OH minus. So then who has the highest concentration here? OH minus, because it was added in excess, but why? Why didn't it bond with any H pluses? There were no more, right? That was technically like my limiting reagent, because I ran out right here. Okay, I ran out of H pluses. They're gone. They've been consumed by the formation of water. As I continue to add OH minus, they just hang out in excess, right? But who else is still here in excess? Sodium ion in true excess, right? Who's just here still hanging out as a spectator? Chloride ion. But who's not present? Hydrogen ion. And a lot of times we omit water from our pictures because water is there all the time, right? And it would just kind of clutter our diagrams. Megan?
If you have like a more dilute solution, how would that impact the curve?
It would be shifted this way. It would require lesser or more volume, but the moles would stay the same. The equivalence point would stay in the same place pH-wise. It would just be shifted on the y or on the x-axis.
If you're like titrating a say active acid, would it start to form like a bunch of hydrogen extra, or would it just?
It depends on the volumes or on the concentrations, but it would form H. It would, if you added an acid, it would consume the H plus until it got to the equivalence point, and then the excess acid would be remaining after the equivalence point, or hydroniums. JT?
Why is there a cap at the pH level? Like, why can't it just keep going up?
It can technically like go up to like 12, 13 area. It doesn't generally get to 14 only because it's in a diluted solution, and so it's got water. Remember PO or pH or pH, whichever one, it's concentration, right? Moles over liters, and so it's just generally diluted in a lot of water. Because a lot of times the solutions we're using are like 0.1 molar, 0.2 molar, and even if I use like 2 or 3 molar, it's still going to dilute at that point. I'd have to have a really concentrated base to make it 14. Okay, feeling good about this so far? All right, the math part you guys are going to rock. This is the part you guys know because you know stoichiometry. I think I clicked it twice. Start by writing the reaction for this one. What, that's my board continues to hate me. Okay, start by writing your reaction for that one. I think I left you a space, but you know, I sometimes don't. There's a whole back page if you need it. So every time you're looking at a process of titrations, it's still just a stoichiometry problem. It is no different than any other stoichiometry problem. So we have to go ahead and write our balanced chemical equation. And then we have to get to moles of the titrate, or aka the known. And I'm good with using moles or millimoles. I'll kind of stick with what you guys wish. I'm just going to keep flipping back, forth, and forth, though, so you're comfortable with both. Oh, this is being funny. There it is. All right, so Jillian, can you give me started? What's the reaction? HCl plus. Margaret, can you pick up from there? Okay, so a lot of you guys are going to use the H and the OH to make HOH, or we can make water, but I think it's easier to see for balancing purposes if you write HOH. And you said BaCl2? Perfect. Okay, so we got our balanced chemical equation. When you read the information, you can see the question is asking for what? Volume of barium hydroxide, right? Okay, so we know we have to save this information about barium hydroxide for last, because I need to end with that identity, ending with that unit and its identity. So who is the titrant here? Say again? HCl, right? It's the one you know everything about. So we call that the known because you know the volume and the concentration. So that's why it's called the known, because you know everything you need to know. So do you guys want to do millis or normal moles? Millimoles? So you said, oh, normal moles? All right, I'll do the other one. It doesn't matter. I'll do one of both. I am not doing micromoles. Okay, you guys want to do femtomoles? Okay. So we're going to do, we're doing millimoles first. 25 milliliters, okay, HCl, times, how do I write this in millimoles? 0.200. Hold on, don't you, if you're writing milli on top and bottom, meaning like millimoles and milliliters, you don't change the number at all. Neither number. I don't want red. I want purple. Okay. So moles, okay, of HCl, okay, over 1 milliliter of HCl. Notice I did not change this number, and I didn't change anything but adding an M and an M to indicate milli. Okay, so milliliters of HCl cancels. Fantastic. Next. Anybody? I want to get to barium hydroxide, so how do I get from A to B? Mole ratio, right? So 2 or millimole ratio, right? Same story. 2 millimoles of HCl for every 1 millimole of barium hydroxide, and then that cancels our millimoles of HCl. And now all I want is milliliters or liters, but either one, right? Because volume is my question, so I'm looking for milliliters or liters. So how do I want to write this next conversion factor, Kui? 1 milliliter on top. Okay, barium hydroxide solution, okay. 0.5 what? Millimoles of barium hydroxide at the bottom. So tell me how you got this.
So, since we know that they are 0.5 molar of oxide oxide, then, so we try to go to liters.
Or volume.
We know a molar is moles over volume.
Right, so moles per liter, that's how molarity is usually expressed. Doesn't matter. It's a conversion factor. You can flip it and do what you need to with it. So millimoles per milliliter can work the same way. We can flip that. And that's why we've done that here versus at the end doing some manipulation. So here, let's try mental math. Let's try this. Okay. So 25 times 0.2.
That is 0.5.
Okay, hold on. Okay, it should be 5. Think of it like this. 25 times 2 is 50. Back that decimal back up one. 5. Okay, or 20% of 25. How many out of a quarter? What's 20% of a quarter? A nickel, right? So it's 50. It's 5 cents. So that's 5. Okay, 5 divided by 2, 2.5. But then what happens when you divide by 0.5? You're actually multiplying by 2, so those cancel each other out, right? When you divide by a half, it's like floppy dot something. Floppy dot copy. It's multiplying by 2. Copy dot flop. Something like that. You guys have your own terms, I have my own terms. But it's 5, right? It's 5, because this 2 cancels with this 2. 5 milliliters of barium hydroxide. Look at you mental math wizards. Okay. Oh, I forgot, is it 266? There we go. All right, moving on. Can you guys do the next one? Choose millis or moles. Don't care. Make it work. Everybody got this, right? It doesn't matter that it's not a true salt and water, right? Okay, so you got ammonia, HCl, makes technically ammonium chloride, but technically that breaks down because it ionizes, because ammoniums always do. So it definitely makes ammonium, ion, and chlorine ion, but it doesn't matter. What's the ratio? 1-to-1 all the way, right? Don't get tripped up by the fact it's not a double replacement with salts and waters. All right, so where are you guys starting? Where are you guys starting? I think I understand you guys. All right, so are you doing millis?
No.
Okay. So you're starting with your titrate. You're starting with your known. So 39.47 milliliters of HCl multiplied by its molarity, but in millimoles, 0.0984 millimoles of HCl. Noticing I'm labeling the identity, so I'm expecting you guys are too. Don't just put millimoles, because I'll be like, millimoles of what? And then you won't get your credit where it's due. All right, so that's a 7. And then what? Mole ratio, which is a 1-to-1, right? So 1 millimole of HCl for every 1 millimole of NH3. Okay, you get a point for this step on the AP exam. By showing the molar ratio, you get a point. So don't neglect that, okay? And then we're going to what at the end? Concentration? So that's molarity, right? Whatever what? Since we're using millimoles, so it's millimoles over milliliters, right? So I'm just going to multiply by 1 over the volume, which will give me millimoles over milliliters. So the volume is 50 milliliters of the ammonia sample. So everything should cancel. Milliliters of HCl, mils of HCl, millimoles of HCl, millimoles of HCl. Then we have millimoles over milliliters. Check. I'm thinking this is a little bit more challenging, but here's what I'm thinking. So this is about 0.1, right? Let's try to mental math it. It's about 0.1. What's 0.1 times 39? So you're just basically moving the decimal back one. So 3.947. Okay, so 3.947. What's 3.947 divided by 50? So that divided by 100. How are you guys getting 0.8? You're going to do long division. 4 divided by 50 is 0.08. So it should be 0.0777. Yeah. Okay. So the answer, you guys should challenge yourselves occasionally. Maybe not every question, but you should continue to try. That is our sig figs there. What's the correct sig figs? What's that? On the mental math?
I did not get the answer.
Unless I wrote.
Yeah, you did 0.1 rather than 0.01.
But I would round that up to 0.1. If I were to round that.
Oh, yeah.
Can you double check that there's a 0 in your work there?
Yeah.
Okay, this is correct. I mean, I got this. All right, we're moving on to the harder ones. Okay, back with me. I think I've got 2 or 3 more I'm going to solve with you, okay? 2 more. Let's start with that. Write your reaction down first, and then let's get started on where we think we got to go. Well, I take attendance because I got yelled at 2 days in a row. The struggle is real. Okay. All right, Chase, get me started. What's your reaction?
So, Fe2O3 plus HCl yields FeCl3.
And water. Okay. Balance, or everybody take a second and balance that. And I'm going to make one addition. I'm just going to put solid here. So you remember that's a solid. It's usually the solids I trip this up in the end, so make sure it's S for solids. All right, so what's our balanced equation? 6 on the HCl. Okay. We got that. We can balance. Check. And then we have, looking at this first bit of information, what stands out to you? What kind of problem is this? Say again? Before, during, after a K-limiting reaction, or limiting reagent. How do I know this? Okay, so you have a concentration information for HCl, but that doesn't come alone, right? You have information about iron 3 oxide. So because you don't know which of those is going to be used to make our products, you've got to figure out who the LR is first. So step 1, we got to do what? get both of them to moles, right, Jaden? Okay. So I got your molar masses just for information for you. So 5 grams of iron 3 oxide weighs 159.7 grams. Okay, so this before the reaction begins, you have, oh, I went to millimole. No, I'm going to stick with moles. 0.0313 moles of iron 3 oxide. Okay, so I'm just going to put a little line here so I can segment my work, but just you guys don't have to do that if you don't want to. How would you get the moles of hydrochloric acid? Multiply M times V, right? Molarity times volume, but volume in this case I'm doing for straight moles, I gotta have it in what? In liters, right? So I'm gonna do 0.50 molar, I'll actually write it out, moles per liter, times 0.020 liters, and that gives me 0.01, yeah, moles of FeCl3. I mean, sorry, of HCl. Okay, so this is how much I have before the reaction of iron 3 oxide. This is how much I have before the reaction of HCl. How much do I have before the reaction for these two? 0 and 0, okay? Alright, so take a second, figure out your LRs. Do it in your head, you're not writing anything down. Try to eliminate that step so you're not correctly using a number you don't need to. Here's your LR. Definitely, right? So this divided by 1 is the same. That divided by 6 is definitely less than that. So regardless, you know your LR is HCl. Okay, so this is an excess. All right, so how do I approach this from here? Subtract which one? So divide or subtract the 0.01 moles of itself. And as some people like to write the 6 to 6 ratio just to represent itself, but you don't have to. We're subtracting 0.01 in a ratio of what? 1 to 6, right? 1 of itself for every 6 HCl's. We're adding, who matters here? Does water matter? No, our question was about like the concentration of something else at the end. So I'm going to add 0.01 moles. I missed some sig figs. There's some extra zeros. Was it 50? Was it 0.5? Was it 00? 2 O's? So these are all 0 zeros on the end, just so I'm not inconsistent. Okay. All right, so this is a ratio of what to what? 2 to 6. Okay, so that's during the reaction what's happening. I'm just ignoring water because it's not actually relevant to the question. You guys could do it if you wish. And then you have 0 of your HCl left over. You have what of this left over? I can math for you. 0.0313 minus a sixth of 0.01 should leave you with 0.0296 moles of Fe2O3 solid. I'm writing solid there so it stands out when I start to look at the analysis side of things. This is made in a 2 to 6 ratio, so you're making 0.333 moles of iron 3 chloride. And then blah, blah, for water. Alright, you guys getting a little bit better at these? Get a little faster at these? Once you practice them more, you're doing good. And that's on our test because we did it with ion concentrations and now with titrations. Okay. What was this question? We got the take. Concentration of iron 3 left over concentration of F3 when all the HCl is reacted, and the mass of iron oxide, iron 3 oxide not reacted. You guys can do that, and then we'll check. Yeah, Queen.
For the ions, iron.
Mhm. Solid stays solid. It does not ionize. One 159. 159.7. How are you guys getting your iron 3 plus? What are you guys taking into account? Okay, so just the 0.003, because this is the only form of iron that's going to become aqueous and become able to ionize. So this makes 1 ion for every 3 chloride ions, right? So I'm asking you for the iron, so it's an easy step because it's a 1-to-1 with itself. But if I asked you for chloride, you'd have to do a 3-to-1 ratio with that compound, or with that mole there. So we're just going to take that number as is. So 0.00333 moles of iron over what? 20, I got moles here, so we have to actually use 0.02. It was 20 liters, right? Or 20 milliliters. Okay. So there's our moles per liter, which would give us what? 1665. So then we would convert, or we'd round that using our 368 rule here to what? 167. And that's iron. And you probably could figure it out. What would I do with this if I wanted to get to the chlorine concentration? Say again? Right, it should be 3 times the amount just because the chlorine's in the same volume, so it's going to be multiplied by 3. Yeah.
So you don't, when finding the concentrations, you don't include the balance, like how the other two inside it?
Correct. Because that was just the recipe to make the reaction happen. But now we're concerned about what's left over, and we just take into account how it dissociates if it were to dissociate. And round that to our 6 figs here, 4.73 grams of the solid. Yeah. This is from the total, and this is always the case. We always take the total volume of the solution. When we look back at the very top, we had only 20 milliliters of the solution. The oxygen is grams, so it was just 20 milliliters. We converted to liters. All right, one more. Ready? I think one more. I'm going a little slow to make sure you're with me, and I know it's Friday. New information on Friday is like, ugh. Okay, so start off by doing what you should do. Yeah, L. Water going L. Yeah, I'm going 5. You guys see this whole thing. You don't need me.
the later side? Probably. Which they think. 0.698 and that's for HCL.
On this, I'm adding one advanced question. Find the pH of the resulting solution. Okay, so at the point where you're getting really good at BDAs, whenever you have two reactants given to you with both information, you have to do a limiting reagent. Because if not, you don't know what the products are being controlled by. You also don't know how to figure out what's remaining in solution until you subtract out your limiting reagent. So since this is a 1-to-1 to 1-to-1, this is a pretty easy one to do BDA style. With me right now, guys? With me? Okay, so once you get your 8.1 millimoles, I did millimoles so I don't have to convert to liters. You find your KOH as your limiting reagent. That means there's no excess phase left over. So immediately you should have known it was going to be an acidic solution at the end. Who thought that pretty quickly in the process? Now do you see that if that is limiting reagent, there's no more strong base, but there is excess acid, you should have an acidic solution. But then I added the caveat, we got to find the pH ourselves, right? So this is a salt. A salt, in our cases right now, doesn't really contribute to pH, okay? This is water. Water, it does not contribute to pH because it's just there to kind of dilute the solution. The excess, or the limiting base, of course, doesn't contribute to pH, but this extra HCl definitely contributes to pH, right? So I'm going to take this and be able to find pH, right? So just as a reminder, what's our pH formula? Negative log of concentration of H+. Well, where's H+ coming from? From this HCl. Well, how do I get the concentration of this H? Say again? Okay, I can do the internal ratio first. So, okay, so if I had HCl, it breaks down into H+ and Cl-. Okay, so this millimole for HCl is the same as the millimoles for H+. Okay, but still doesn't give me to molarity. What's our total volume? 95 mils, right? 45 to 50 milliliters. So we're going to take our millimoles, divide it by our 95 milliliters total to get our new diluted concentration. Because it was super concentrated, it was 0.2 molar, but it's not that anymore because now it's blended with some more aqueous solution. So I'm just going to kind of do this right here. 1.9 millimoles of H plus over 95 milliliters is what? 0.02? Is that what you said? I like to pretend I can hear you. 0.02, is there anything else? No? Okay. Okay, so this information goes in here. So then we do negative log of 0.020, which I think this concentration, let's double check our numbers. 3 sig figs all the way, so this should be 200. Okay, and then what's that? What is that in terms of pH? 1.699. Okay, which is acidic, so we know we're on the right side of the scoreboard, right? So now we're right here. And then how is pH sig figs controlled? So the decimals, so the pH sig figs are within the decimal of itself, but who controls how many decimals there should be? The concentration, right? That's why I wanted to verify we were following through with that. This has 3 sig figs in its concentration. This has 3 decimals, which is how we interpret the sig figs within our pH. Yeah. So this is an example of a one-to-one. Listen up, guys. Good question. If this were, let's say, basic, we had a basic solution, and we had calcium hydroxide in our excess. Okay. If that were the case, how would I get hydroxide ion moles? I won't multiply by 2 because it's an internal ratio of 2. So if this was like 2 millimoles of said calcium hydroxide in excess, then I would then say calcium ion and 2 hydroxide ions are forming from that dissociation of that. So instead of being 2 millimoles of OH minus, it would be 4 millimoles of OH minus, which then I would take that information, and how would I get concentration of OH minus? Divided by total volume, and then we would get our OH minus and then backtrack to pH. You will have something like that eventually, yeah. So I had to go back kind of to my originals, because when you're subtracting, this I wrote as, I probably could go back and adjust my VBA. This would be 1, 2, 3, 1, 2, 3, so when I multiply it should be 3. So sometimes in the middle of BDA, I'm less cognizant. So then when you pull down those zeros, it should be 3. Okay? And this is 95.0 with the 45.0 and the 50.0 milliliters. From the molarity, that's going to be 3 sig figs, because the way it works is the decimal is present, then you start from the Pacific, and you start counting sig figs at the first non-zero digit. So not the 0, not the 0. 2, 0, 0 are my 3 sig figs. Okay. Quick review from Honors Chem. Yeah. Basically at the beginning, yeah. It's usually based on what our measurements were to begin with, but they were all 3 sig figs, so it was really easy. But if one had 1 sig fig and the other had 3 sig figs, you stick with 1, because the lowest sig figs controls your final answer. Yeah. Say that again. Mm-hmm. Yeah, if they're all the same. Yeah. All right, so let me pause for a second. You guys have maybe about not quite 30 minutes left with me, and I don't think that we're going to do our lab today. So, no, you need to do a pH hitting point. I have to prioritize with myself. Okay, so at the lab stations, I've already put these assignments out for you, and the idea is that you can take information from at any point during a titration, and you can find the pH from that, just like we did in this last problem. You can take at any point in the titration and find the exact pH. So I will have given you a situation, and I will have given you the volume of the base added or said titrate, whichever one it is, and I want you guys to take this information and the information I've given you at the top, and at each point tell me how many moles you had of each, and then the pH that would be resulting because of that. But note to self, at what point in time do we have equivalent moles of acid and moles of base? at the equivalence point, but you don't know where that is here, right? So you have to find the moles of each. If one is in excess, just like we just did, take those moles you got at the excess, divide it by your total volume. That will help you get to the point where you can then find pH from that, okay? So I'm gonna let you guys work in teams of 3 or 4. I've got 7 assignments out. Go ahead and get started, okay? You don't have to write it on my paper. You do not have to write it on my paper. I'm just giving you the assignment back there. So listen, okay, 3, 2, 1. I have 50 papers on here. You're probably just gonna write on a separate sheet of paper because this isn't gonna be big enough for everybody's work. But what I would do is when you get to your group, assign 2 or 3 boxes to that person. And then at the end, when you get all your keys, you go through and sketch your titration curve. I'm calling it the lab grade because it's the equivalent in terms of practice for lab, but don't put me wrong with it. Okay? So, get it under. Are you 3 or 4? Guys, I could have assign your group, and you guys can make 3 and 4. Make 3 and 4. Get it together. Great, you guys got 3. You guys got 3. There's only 7 assignments there. You have to split it. You guys got 3. They have 2. One person go there. They have 2. One person go there. 3 times 12, 3. Yes, got this. I know we only have like 5 minutes left in class. Let me give a little bit of time.